Hi, my name is Dwayne Dortch, and today we're going to talk about long tasks. Long tasks are JavaScript code that monopolize the browser's main thread for more than 50 milliseconds. Long tasks cause the user interface to freeze, making the page unresponsive to user input, even if it looks ready. Clicks and taps often don't work because event listeners and click handlers have not yet been attached. As a result, users start to notice that their clicks are delayed and that scrolling the page has become janky or unresponsive. Long tasks can have an adverse effect on other key performance metrics, including the new Core Web Vital metrics like largest contentful paint and first input delay, as well as time to interactive, which measures when the page is ready to respond to user input. A metric that directly measures user frustration is rage clicks, which measures moments of repeated clicks or taps with no response. Rage clicks can be measured in real user monitoring tools like Akamai's Impulse. Of course, this excessive CPU work caused by long tasks is going to drain batteries, and that's never a good thing as users look for ways to extend their battery life throughout the day. One of the ways to check for long tasks is in Chrome DevTools. First, open DevTools and go to the Performance tab. Next, record a profile of loading the page. Notice a row of blue bars labeled Long Tasks. The striped line indicates the amount of execution time that exceeds the 50 millisecond threshold. A long task that jumps out to me is this one that is much longer than the others. This task is concerning because it occurs between first contentful paint and largest contentful paint. In fact, there's about a 600 millisecond gap between these two important timers. Shortly, we'll talk about how the location of long tasks impact Core Web Vitals and the user experience. Long tasks are also visualized with gray bars in the main thread section. Long tasks are shown with a red flag in the upper right corner. Hovering over a task reveals details about the duration of the task and if it was considered long. Clicking on the task enables the detail pane at the bottom of the screen. The Summary tab shows where the time is spent and total blocking time. The Bottom-up tab provides additional useful information. Select Group by Activity. This allows you to see what activities contribute most to the task taking so long. You can also group the view by URL to quickly determine which scripts are causing the issues. You can also group by domain or subdomain to reveal the domain names responsible for the violations. This is useful for isolating issues with third-party scripts. Another CPU metric related to long task time that's useful to track is total blocking time. DevTools reports total blocking time at the bottom of the Summary tab. It's important to understand what this metric is and what it's not. Total blocking time measures the total amount of time between first contentful paint and time to interactive where the main thread was blocked long enough to prevent user input. So the blocking time for any single task is its duration in excess of 50 milliseconds. And the total blocking time for a page is the sum of the blocking time for each long task that occurs between first contentful paint and time to interactive. Well, let's look at an example. In the first example, we see 6 tasks ranging from 30 to 140 milliseconds in duration. Only 2 of these tasks exceed 50 milliseconds, the 140 millisecond task and the 60 millisecond task. So only they would be considered long tasks. The 140 millisecond task exceeds 50 milliseconds by 90 milliseconds, and the 60 millisecond task by 10 milliseconds. So the total blocking time is 100 milliseconds, the 90 plus the 10. Any long tasks that happen before first contentful paint and block the page from rendering are not included in total blocking time. So total blocking time is not, in fact, the total blocking time for the page. It's better to think of it as the blocking time after start render. Total blocking time is a great companion metric for time to interactive because it helps quantify the severity of how non-interactive the page is prior to becoming interactive. It's not only important to understand the amount of long task time, but it's also important to understand where on the page the long task time is taking place. As we saw in the previous example, our largest long task time occurred between first contentful paint and largest contentful paint, resulting in a larger than desired time for these Core Web Vital metrics. If JavaScript isn't critical for the rendering of the page, simply move it to later in the page load. The total scripting time may not change, but the time spent before some of the key timers may improve dramatically. Let's talk about a few ways to optimize long tasks and improve the user experience. First, the JavaScript you write is nothing like the code that's actually executed. Modern browsers use JIT compilers and various optimization techniques to try to give you the fastest possible execution, and this can substantially change the dynamics of the code you've written. Use the DevTools profiler to understand how your JavaScript is executing in the browser so that you can make appropriate changes as needed. Second, large scripts are often a major cause of long tasks, so consider splitting them up into smaller chunks that run within 50 milliseconds. Third, run scripts at the right time in the right place. We've seen how key user experience metrics can be impacted by the placement of JavaScript on the page. Fourth, keep an eye on those third-party scripts. Their long tasks can delay vital content from becoming interactive. And finally, evaluate your code in idle periods using Philip Walton's idle until urgent, which is a very cool model for executing JavaScript during periods of idle CPU. In summary, keep your pages responsive. Minimizing long tasks is a great way to ensure your users have a delightful experience when visiting your site. Thanks for joining us today.